really haven't talked about, they create pull, but all of these, because they're ions, they can break apart in water, they have more pull. But if you're talking about saturated fat, lipids, glucose, sucrose, cellulose, any of those, they don't break apart like this. They don't have as much pulling power to pull water.
The sodium chloride is they break apart because it's sharing electrons?
They actually transferred to complete their outermost orbitals, and that's why they break apart. That's just the nature of an ionic compound, is to break apart into ions in water. So that's why they break apart. These are sharing, so they're less likely to ionize because they're not transferring electrons. Colin.
Is this on your PowerPoint?
Yeah. Do you understand what I mean by pulling power? Okay, because if you've got more solutes, we know from osmosis, if you have more solutes in a particular compartment, those solutes are going to create movement of water to that area of solute concentration. So that's what I mean by pulling power. These types of ions here are going to attract water to their areas, whether it's intracellular or extracellular, in order to equalize concentration. Things like glucose do have pulling power, as you might have recall back from our urinary system, but it's not anywhere equal to the pulling power of all these ions. I guess it's what you would think of as collective force, because the more ions you have, the more attraction of water is going to be to that particular compartment.
Less power with the organic covalent.
Yeah, simply because you've got they're one unit and they don't break apart into multiple units.
That clicks me.
Okay. Instead of talking through all of these little, I got 4 of them on page 130. Instead of talking through all these 4 on page 130, I thought I'd hit the highlights for you. On page 130, what I've done is summarized for you the 4 most common types of ions here. Anything that's in bold on this chart is something that I would look at. I wouldn't memorize the chart. I definitely would not memorize the normal levels in solution. For instance, it says under sodium, normal level is 142 milliequivalents per liter. Don't memorize that. That's a reference number you can look up if you need it, but I just put it there just kind of as a reference point for you. I would know, however, that sodium is actually the most abundant cation in our ECF. What's ECF? Good. Extracellular fluid. So we're talking about fluids outside the cell, not inside. So it's our most abundant cation outside our cells. The next bolded item is under reabsorbed and regulated by. Notice aldosterone is bolded there. This is just a review for you from back in chapter 24. Aldosterone does help move sodium in, but what portion of the nephron? DCT or PCT? DCT. Good. So aldosterone is necessary in the DCT.
Before that happens, you release renin and then angiotensin to make the aldosterone active?
Exactly. It's a renin, angiotensin 1, angiotensin 2, and then aldosterone.
Okay.
Sure. To release aldosterone, you have to go through this domino effect. You release renin first, then angiotensin 1, angiotensin 2, and then finally aldosterone is the last of that list. So renin, angiotensin 1, angiotensin 2, and then aldosterone. And then for one question, it's just how it's regulated.
It's just a note on 130 in relation to sodium.
Yeah, talking about aldosterone secretion at the DCT. So she was asking, how do you get to releasing aldosterone? Stephanie, that? Okay. Another bolded term there for you is hypernatremia, and hyper, of course, is excess or too much. So hypernatremia means we have excess salt in the bloodstream. So as we learned previously, what does excess salt do to your blood volume and blood pressure? Yeah, increases both of those items. You'll notice here that both sodium problems, and this could be dietary intake, this could be just having a diet full of sodium, that can cause hypernatremia. In addition, aldosterone problems could also cause hypernatremia. So in some types of blood pressure medication, the blood pressure medication suppresses some part of that aldosterone mechanism, and that actually suppresses the amount of sodium that a person can reabsorb back into the bloodstream. So, some blood pressure medications are not alpha blockers or beta blockers. Some are part of this aldosterone mechanism blocking, and that helps to reduce sodium content in the blood. So hypernatremia can lead to excess fluids in the bloodstream. What about hyponatremia? Yeah, if you drink a bunch of fluids that are hypotonic, such as just plain old water, that will flush out your sodium. That will give you a case of hyponatremia. And hey, hyponatremia means you lose your fluids, or rather you lose your sodium as you're washing it away in your fluids. The problem here is it really causes an imbalance in your water compartment. So no longer do you have a way to maintain homeostasis. You've essentially lost your major extracellular cation. So hyponatremia can be caused by excess fluids, perhaps drinking a bunch at a short period of time. Or you might notice here, actually not on this picture, but going back again to aldosterone, if you don't have enough aldosterone, you can actually promote hyponatremia. Too little sodium in the extracellular fluid. So perhaps it could be caused by diet and drink. It also could be caused by aldosterone issues.
Said the hypo was too much, or
too much fluid but too little sodium.
But the aldosterone.
Oh, too little aldosterone.
And for the hyper, what was it about the aldosterone?
For hypernatremia, it would be possibly excess aldosterone or too much aldosterone. Table salt is sodium chloride. So here you go with chlorine. Chlorine is an anion, carries a negative charge. It is the most common anion in our extracellular fluids. You might wonder why we haven't really talked so much about chlorine, if it's so common. It is one of the major players for forming stomach juices, especially hydrochloric acid, as you can see here. It forms with those hydrogen ions to form that, really strong acid in our stomach. Chlorine also helps to regulate osmotic differences, meaning where the fluid stays, whether it's outside the cell or inside the cell. Again, aldosterone is the regulator for this one because when we talked about sodium reabsorption in the nephron, you might recall that chlorine automatically follows if sodium is being reabsorbed. Okay. There can be problems, though, called hypochloremia. If a person has excess vomiting, okay, hypokalemia, excessive ingestion of alkaline items, Tums, what else, Rolaids, Alka-Seltzers, that kind of thing, can get you into an alkaline situation. Hey, even aldosterone deficiency again. Those types of situations can put a person at a state of hypochloremia. So not having enough chlorine in your bloodstream, again, messes with forming enough chlorine for your stomach juices. But probably most important here is not having enough chlorine to maintain water balance in the compartments outside your cells. So if you know somebody who pops Tums or Rolaids or Alka-Seltzers like it's candy, this could be a situation because you're putting the body more into an alkalosis state. That's kind of touching on Thursday's topic with, discussing acid-base balance. All right, so potassium we've talked extensively about in Bio 210. This is the most abundant cation in the intracellular fluid. You might recall this one's necessary for maintaining resting states for both nerves and muscles. But more importantly, in terms of today's discussion, it's also important for maintaining fluid balance. The volume of fluid inside your cells relies heavily upon having enough potassium in there. Interesting concept to think about here. We've talked off and on all semester about ways to maintain blood pH. We're now getting into the topic where we can hit that head on with acid-base balance on Thursday. But I wanted to show some this kind of little trick here to you about acid-base balance. Let's talk about the first bullet point there. It says in acidosis, potassium moves out of the cell and there's an old friend, hydrogen moves in. All right, blood pH needs to be what? 7.35 to 7.45. You might recall from our respiratory discussion that carbon dioxide combines with water. It forms a middleman known as carbonic acid. Carbonic acid is an unstable middle agent, so it quickly dissociates or breaks apart into hydrogen ions and bicarbonate ions. So if you have excess hydrogen ions in the bloodstream, what does that do to your blood pH? Drops it, sends you below 7.35. Let's say that you're currently sitting at a blood pH of 7.1. You've got too much hydrogen ion in the bloodstream right now. We've talked about how your kidneys can secrete more hydrogens to get rid of it more quickly. We've talked about how your respiratory system can speed up breathing rates so you